We will start in 1 minute. Today we'll continue in section 1110 on Taylor and Maclaurin series. So here are the forms for the Taylor series of a function f at a, and also the Maclaurin series of a function f. The coefficients of a Taylor series at a are the nth derivative of f evaluated at a divided by n factorial. And then the binomials are x minus a raised to the exponent n, starting with n equals 0. The Maclaurin series of a function f, that's just a Taylor series at a equals 0. So for a Maclaurin series, the coefficients have the form the nth derivative of f evaluated at 0 divided by n factorial. And then we don't have a binomial here, we just have the variable x to the n. Okay, we'll review a little bit about what we found out about Maclaurin series for certain functions like e to the x. So the Maclaurin series for e to the x is 1 plus x squared divided by 2 factorial plus x to the third divided by 3 factorial, and so on. And in sigma notation, this is from n equals 0 to infinity. And the terms are x to the n divided by n factorial. The radius of convergence for the Maclaurin series for e to the x is infinity. So this Maclaurin series works for all values of x for e to the x. The Maclaurin series for cosine of x. This one is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So in sigma notation, from n equals 0 to infinity, it's an alternating series, so -1 to the n, and then we have x to the 2n divided by 2n factorial. The radius of convergence for the Maclaurin series for cosine of x is also infinity. Okay, for sine of x, the Maclaurin series starts at x, then it's minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial, and so on. So this is also alternating. So sigma starting from n equals 0 to infinity, -1 to the nth. And this time the terms are x to the 2n plus 1 over 2n plus 1 factorial. Yesterday when I wrote this, I started at n equals 1. It's okay, but if n equals 1, then the exponent is 2n minus 1, and the factorials are 2n minus 1. And then you have to write -1 to the n minus 1. Either way is okay. This is perhaps more conventional. The Maclaurin series for 1 over 1 minus x. Well, we know what 1 over 1 minus x looks like as a geometric series. And I checked, and the Maclaurin series for 1 over 1 minus x is the same. So the Maclaurin series for 1 over 1 minus x is 1 plus x squared plus x to the 3rd, and so on. And the sigma notation, n equals 0, from n equals 0 to infinity, and the terms are x to the n. The radius of convergence for the series of 1 over 1 minus x is 1. Remember, the absolute value of x is less than 1, so the radius of convergence is 1. And I skipped the radius of convergence for sine of x. It's also infinity. Okay, what's the Maclaurin series for 1 over 1 plus x? It turns out that it's the same as the series you get if you use the geometric series formula. So this one is 1 minus x plus x squared minus x to the 3rd, and so on. So in sigma notation, from n equals 0 to infinity, it's an alternating one, so -1 to the nth times x to the n. The radius of convergence for this series is 1. Okay, what about the natural log of 1 plus x? The derivative of the natural log of 1 plus x is 1 over 1 plus x. 1 over 1 plus x, yeah. So the natural log of 1 plus x can be found by integrating 1 over 1 plus x. So if we just find the antiderivatives of the series above that, and then add the integrating constant c, we get c plus x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, and so on. So in sigma notation, so let's start this one at n equals 1. Oh, there's a c plus that comes out, c plus the sigma notation. So if we start the series at n equals 1, we have negative 1 to the n minus 1. And x to the n over n. We can show you, we've done this before, but we can show that the integrating constant has to be 0. If you replace x with 0, we get the natural log of 1. The natural log of 1 is 0, but if you replace all of these x's with 0, we're just left with c. So c equals 0. Okay, another one, 1 over 1 plus x squared. We saw how to get us infinite series for 1 over 1 plus x squared, interpreting it as a geometric series. And its Maclaurin series is the same. So this is 1 plus negative x squared to the first plus negative x squared to the second, and so on. So if we simplify those a little bit, we get 1 minus x squared plus x to the fourth minus x to the sixth, and so on. So in sigma notation, start out at n equals 0. It's alternating, so negative 1 to the n. And the terms are x to the 2n. Okay, finally on this page, an infinite series for the inverse tangent of x. So how do we do that? Yeah, the derivative of inverse tangent of x is 1 over 1 plus x squared, or thinking of it in the other direction, the indefinite integral of 1 over 1 plus x squared dx is inverse tangent of x plus a constant. So we have the series for 1 over 1 plus x squared, so we just find antiderivatives of the term from the Maclaurin series for 1 over 1 plus x squared. Okay, so we'll include the constant of integration and then write down the antiderivatives from the series above. So we get c plus x minus x to the third over 3 plus x to the fifth over 5, and so on. So c plus, and then in sigma notation, from n equals 0 to infinity, alternating series, so -1 to the n, and so the terms will be x to the 2n plus 1 over 2n plus 1. So let's check to see if that works. When n is 0, we get x to the first over 1. And the term is positive when n is 0. When n is 1, the term is negative. 2 times 1 plus 3 is x to the third over 3. So that appears to work. And the radius of convergence for each of those is also 1. Okay, so most of these, it seems to me most of these are pretty easy to remember. Like the first 5 are pretty easy to remember. And you can derive the next 3 just by integrating, and 1 over 1 plus x squared, just use the geometric series form to find a series for that. Okay, next page. Okay, find the Maclaurin series for f of x equals the binomial 1 plus x to the k, where k is any real number. So this will take a little bit of writing. So on a separate piece of paper, we'll look at find the Maclaurin series for the binomial 1 plus x raised to the k, where k is any real number. Okay, so if f of x is 1 plus x to the k, see, what are the coefficients for the Maclaurin series, if it's a Maclaurin series for a function f? So c sub n just represents a coefficient in the series. So it's the nth derivative of f evaluated at 0 divided by n factorial. Yeah, that's right. From the very first page, I have both the Taylor series and the Maclaurin series, and you can see what the coefficients are there. Okay, so let's find the first few derivatives for f of x. The first derivative what's the first derivative of 1 plus x to the k? Yeah, we just used the power rule and the chain rule, just as a reminder. So k times the quantity 1 plus x to the k minus 1. And just as a reminder, we want to multiply this by the derivative of the expression inside the parentheses. So the derivative of 1 plus x is just 1. So I point that out just as a reminder in general, but from now on, we'll omit doing that since it's going to always be 1. The second derivative is k times k minus 1 times the binomial 1 plus x to the k minus 2 times 1. The third derivative of f is k times k minus 1 times k minus 2 times the binomial 1 plus x to the k minus 3. And so on. You can probably see the pattern. So the nth derivative of f of x, well, it's going to be k times k minus 1 times k minus 2 dot, dot, dot. So what comes after that? The last constant factor before we multiply by 1 plus x to the k minus n. So let's go back and see if we can see what the pattern is. The third derivative of f, the exponent on the binomial 1 plus x, is k minus 3. 3 is the same as the particular derivative that we're computing. And the factor that's closest to 1 plus x is k minus 2, where 2 is 1 bigger than 3. So maybe that helps.
K minus n plus 1.
Yeah, k minus n plus 1. Okay. So when we evaluate each of those at 0 for the Maclaurin series, we can write down what the coefficient is using this. So when x is 0, this term just becomes 1. And so we're just going to be left with k times k minus 1 times k minus 2 and so on. And the last factor is k minus n plus 1. And we're dividing it all by n factorial. So a couple of things to note that might be useful. I'll point this out again in a few minutes. But the number of factors that we're multiplying in the numerator is the same number as the factorial that we have in the denominator. So in the numerator, we have n factors, and the denominator is n factorial. Okay, so term by term, the Maclaurin series is 1 plus k over 1 factorial times x to the first. What's the next one? Yeah, k times k minus 1 over 2 factorial times x to the second. So note that the number of factors in the numerator is the same as the number that we're taking the factorial of. And then the next one, k times k minus 1 times k minus 2 over 3 factorial times x to the third, and so on. Okay, so in sigma notation, from n equals 0 to infinity, well, we just write k times k minus 1 times k minus 2 and so on up through k minus n plus 1 over n factorial times x to the n. Okay, this is referred to as the binomial series. So going back to the other piece of paper, we'll write down what we just found. Okay, the binomial series. So the Maclaurin series, or the series for f of x equals 1 plus x to the k, is what we just found. Infinite series from n equals 0 to infinity. And the coefficients are k times k minus 1 times k minus 2 and so on. The last factor is k minus n plus 1 over n factorial times x to the n. Okay, so there's a notation for the coefficients. For more specifically, the binomial coefficients. So the notation, we have a set of parentheses, the top number k and the lower number n. This special notation represents this, what we have written. So in combinatorics, this particular notation is used quite a bit in a more restricted setting. But for convenience, this binomial coefficients, k choose n, is k times k minus 1 times k minus 2 and so on, up through k minus n plus 1, all divided by n factorial. So when we encounter this, n is always going to be an integer starting at 0 and then increasing by 1 at a time. But the number k can be any real number. So here's a little bit more about the binomial coefficients. So what would we get if we have 7 choose 2? What does that look like? Well, in the numerator, we start with 7, and then we multiply 7 by the next integer less than 7, which is 6. How do I know when to stop? Well, the lower number, 2, determines how many factors I have. So 7 times 6, I stop. And then the denominator is 2 factorial. See what I mean? And then, of course, this can be simplified, but this is how you would get started. In combinatorics, the number k is always an integer that is greater than or equal to n. And we might encounter that, but just as an aside, that might help. If m and n are non-negative integers and m is greater than or equal to n, this means m factorial over n factorial times m minus n factorial. Maybe you've seen that before. So that's exactly what happened over here. We can verify that. 7 choose 2 using this formula. So this should be 7 factorial divided by 2 factorial times 7 minus 2 factorial. So do the arithmetic a little bit. 7 factorial over 2 factorial. 7 minus 2 is 5 factorial. 7 factorial is 7 times 6 times 5 factorial, and we're dividing by 2 factorial times 5 factorial. And 5 factorial divided by 5 factorial cancels. So we're just left with 7 times 6 divided by 2 factorial. Okay, but for our purposes, this number k can be anything. So what if we had instead, say 3/4, and with the number 3 below it? How do we make a number out of that? Well, in the numerator, we start with 3/4. Then we multiply that by 3/4 minus 1. 3/4 minus 1 is negative 1/4. Well, the denominator determines how many factors we need. So the next number is negative 1/4 minus 1, which is negative 5/4. And now that I have 3 factors, the denominator is 3 factorial. Might take a little getting used to, but it's not so bad if you practice it a little bit. Okay, so let's try it out. Use the binomial series to find the series expansion of 1 minus x to the negative 1. Okay, keep in mind, though, we derived a formula for the binomial series for 1 plus x to the k. So we're going to rewrite this. Instead of 1 minus x, we're going to think of that as 1 plus negative x. And then the exponent is negative 1. Okay, so the binomial series. Well, when n is 0, we have k over n when n is 0 times x to the 0. Sorry, I messed up already. Times negative x to the 0, because we're replacing every x with negative x. And then what's the next term? Negative 1, choose 1, times the term negative x to the first. Then what?
Negative 1, choose 2.
Yeah, negative 1, choose 2, times negative x to the second. We'll just do a couple more. And then negative 1, choose 3, times negative x to the third. Negative 1, choose 4, times negative x to the fourth, and so on. Okay, negative 1, choose 0, that's just 1. Negative x to the 0 is 1, so we get 1. Then the next term, negative 1, well, we have one factor. The factorial is 1 factorial, and 1 factor is just negative 1. And then negative x to the first is negative x. Hey, what's the next coefficient? What's the coefficient for the x squared term? Well, negative 1, choose 2. That means negative 1 times negative 2 over 2 factorial. And then negative, the term negative x squared is just x squared. Then the next term, negative 1, choose 3. What does that mean?
Negative 1 times negative 2 times negative 3 over 3 factorial.
Yeah, negative 1 times negative 2 times negative 3 over 3 factorial. And then negative x to the third is negative x to the third. We'll simplify further in the next step. And then the next one, negative 1, choose 4. That means negative 1 times negative 2 times negative 3 times negative 4 divided by 4 factorial. And the term negative x to the fourth is positive x to the fourth. Okay, in the next step, we can simplify everything. 1 plus negative 1 over 1 times negative x is just plus x. What's the next term?
2x squared over 2 factorial.
Yeah, -1 times -2 is +2 divided by 2 factorial is 1. So we get plus x squared. What's the next term?
X cubed.
Plus x to the third. Yeah, -1 times -2 times -3 is -6. But negative x to the third is the negative of x to the third. So it's +6 over +6, which is 1. And so we get plus x to the third. And then the last one in our test,
X to the fourth.
yeah, x to the fourth. Gee, where have I seen that series before? 1 plus x squared plus x to the third plus x to the fourth. Maybe you saw earlier 1 minus x to the -1 is just 1 over 1 minus x. But this is an alternative way to find the series using the binomial series. So that's what we did. 1 minus x to the -1 is the same as 1 over 1 minus x, which is just the series from n equals 0 to infinity of x to the n. Okay, the next example will be a little more involved. So use the binomial series to find the series expansion of 1 plus x squared to the 1/3. Let's hold off on this one. Let's go to the next page, and then maybe tomorrow we can do this one. But the next page, this won't be too bad, but if you haven't done it before, this is probably a good time to do it. And it's similar to things that we've done already. Let's use known Maclaurin series to get Maclaurin series for the functions below. So if we refer to our piece of paper that we had earlier, on the first page, the Maclaurin series for inverse tangent of x is x minus x to the third over 3 plus x to the fifth over 5 minus x to the 7th over 7, and so on. So to get a series for inverse tangent of 2x, all we have to do, replace every one of those x's with 2x. So this one, 2x, and then minus 2x to the third over 3, and then plus 2x to the fifth over 5, and so on. So not too bad. Let's take it one step further. When you cube 2x to the third, you get 8x to the third, and then over 3. 2x to the fifth is 32x to the fifth over 5. And then 2x to the seventh is 128x to the seventh over 7. and so on. So let's try the next one. F of x equals e to the 3x minus e to the 2x. So we remind ourselves that e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and so on. So we can write what e to the 3x is and what e to the 2x is, and then just subtract one series from the other. So e to the 3x well, in the series e to the x, we just replace every x with 3x. So we get 1 plus 3x. And let's go ahead and simplify these a little bit. 3x to the second is 9x to the second over 2 factorial. And then 3x to the third is 27x to the third over 3 factorial. 3x, the term 3x to the fourth is 81x to the fourth. And then over 4 factorial and so on. Then below it, we'll write e to the 2x. This time in e to the x, replace every x with 2x. So we get 1 plus 2x. 2x, the term 2x to the second is 4x to the second over 2 factorial. 2x, the term 2x to the third is 8x to the third over 3 factorial. The term 2x to the fourth is 16x to the fourth over 4 factorial. And then the difference, just subtract, combine like terms. Pretty easy, really. 1 minus 1 is 0. 3x minus 2x is x. 9x squared over 2 factorial minus 4x squared over 2 factorial. How much is that?
5x squared over 3 factorial.
Yeah, 5 plus 5x squared over 2 factorial. And then the next one, 27x to the third over 3 factorial minus 8x to the third over 3 factorial is plus 19x to the third over 3 factorial. And we'll just do one more. 81 minus 16 is 65x to the fourth over 4 factorial. So if you had something like this on a test, say like on the final exam or something, this would be a perfectly fine way to leave the answer. If you want to take the time to get it into sigma notation, you can, but I wouldn't bother in this case. Okay, let's get started on this one. F of x equals x squared times the natural log of 1 plus x to the third. So what do we need to do if we want to find a Maclaurin series for that?
Replace all the x's with x squared and multiply by x squared.
Yeah, we'll recall the series we got for the natural log of 1 plus x, and then the natural log of 1 plus x to the third will be found by replacing every x in that with x to the third, and then afterwards multiplying every term by x to the second. So let's see, the natural log of 1 plus x. So that is x minus x to the second over 2 plus x to the third over 3 minus x to the fourth over 4 and so on. Okay, so the natural log of 1 plus x to the third, we just replace each of those x's with x to the third, and we get x to the third minus x to the sixth over 2 plus x to the ninth over 3 minus x to the 12th over 4 and so on. And finally, x squared times the natural log of 1 plus x to the third. We just multiply each of the terms in the above series by x squared, and we get x to the 5th minus x to the 8th over 2 plus x to the 11th over 3 minus x to the 14th over 4 and so on. Well, there's less than a minute. We've spent a fair amount of time on Maclaurin series, but we should do some Taylor series. So f of x equals the natural log of x, and a is 2. So the coefficients, we can at least write that down before we run out of time. The coefficients of the Taylor series, the nth, c sub n coefficient will be the nth derivative of f evaluated at 2 divided by n factorial. But we're out of time, so between now and later today, I'll figure out what we're going to do tomorrow. But that's all for today.